Hello, everyone. Today we'll talk about the work, the concept of the work, and also the work kinetic energy principle in general. Okay, so let's get started. Now, when we talk about a work in general, work is basically defined by the following. So work is basically defined as this here. Okay, so if an object covers certain displacement in the direction of the force, so these are the important terms here. So it covers certain displacement in the directions of the force, then the work is said to be done. Okay, so what about the mathematically, how do we find the magnitude? So the magnitude of work is basically given by the force times the displacement here. Okay, so now consider, so what does it mean? So let's try to understand in a situation where we're pushing a box. Okay. So now let's assume that we are exerting a force F on this box. So if we exert a force F on this box, then let's also say that the box has covered certain displacement here. Okay, so the box has covered certain displacement. So this is S here. And yes, so then the work done is basically, so the work done on the box, okay, on the box is given by the force that you applied on the box times the displacement that the box covers. So this is how we basically define what a work is. Okay, now you may be wondering, does it always have to be the force acting in parallel to the direction of in the direction of the displacement? And the answer is no. You could have applied force at certain angle with the displacement. For example, okay, let us assume the following situation here. So let's say we have a box here. So if we have a box and there is some force that's acting in the box, but this time the force is inclined. So let's say the force is acting at certain angle with respect to the ground. So let's say this is F here. And the angle to the ground is, let's say, theta. Now, when we pull an object with force F with certain angle theta, we know that it still covers some displacement, right? So the box still covers some displacement here. So let's say that the displacement is S here, okay? Now, the way how we define work was this. A work is said to be done if the force applied on an object makes it cover some displacement. So that's how we define the work to be. But we also said that the force and the displacement has to be parallel. So in this case, the force has two components. So one of the component is this one here, right? So this is the horizontal component of the force. And the other component of the force is basically this. So this is the vertical component of the force. Now, when we want to find the magnitude of the force that's applied on this box, we'll look at the horizontal component here, because that's how we define the work to be. Okay, so the work done in this situation is basically then, so the work done is F horizontal times the displacement. Okay, so what is the horizontal force? If we resolve a vector in the horizontal component, then we know that Fh has to equals to F cos theta, right? So therefore, our work done is basically F cos theta times the displacement. Now, if we rearrange it, we can write it as work done equals to force times displacements times cos theta. Okay, so this is how we then define the force, the work, if the force and the displacement has an angle between them. Now, next, let's look at what happens when we, let's look at what's the different scenarios that can that we can have when the theta changes. So when theta equals to 0, we can write work as force times displacement times cos of 0, right? So which simply gives you force times the displacement. Now that's just the way how we define the force, right? So the force and the displacements are parallel to each other. And when theta equals to 90 degree now, so when theta equals to 90 degree, then we know that this is force times displacement times cos 90 degree. But now you do know what's cos 90, right? So cos 90 is 0. So the overall work done is 0 when theta is 90. Now, what happens when theta is 180 degree? So theta, when theta is 180 degree, then we say that this is minus Fs. So let's look at the scenarios for individual cases. So in this case, in the first case, we have a force that's acting in the direction of the displacement, excuse me. So that's S. So this is the scenario for the first case. In the second case, now you could assume a situation where the force is acting upward or downward, right? And it still covers some displacement. In this type of situation, we don't say that the work is said to be done here, okay? So the work is not done in this situation. Even though there is an action of lift, we still don't say that there is a work done here, according to physics. And the last case is basically a situation where the forces and the displacements are in the opposite direction. So this is force here, but the displacement covered is still in towards the right. So this sort of situation can be understood when like you're trying to bring a car to a rest. So let's say this initial velocity of the car is 0 and the final velocity of the car is, excuse me, the initial velocity is u and the final velocity is 0. So in this case, the force has to be done, sorry, the work has to be done by the brakes in order for the car to come to a rest. So there should be some resistive force acting on the car. So this is a situation. These are the three different situations of the work done. And let's move on to the idea of kinetic energy next. Okay. Okay, so when we talk about the kinetic energy in general, it is basically the energy of an object by virtue of its state of motion. Because an object is in motion, it has some energy. Okay, so that energy is classified as kinetic energy. And the magnitude of the kinetic energy is given by Ek equals to 1/2 mv squared, where m is in kg, mass in kg, v is velocity in the meters per second, and Ek is the kinetic energy in the joules. Now, also, kinetic energy is a scalar quantity. So kinetic energy is a scalar quantity. Okay. The reason being that the energy, the kinetic energy is a state, it's the energy possessed by its state. So in this case, by a virtue of its motion, it's the energy stored in that object by virtue of its motion, right? So it does not matter in which direction an object is moving. If an object is moving in certain velocity, it will always have that energy stored in an object. Okay. And also, the other thing is we have a velocity squared here, right? So you might wonder that velocity is a vector quantity. So why is kinetic energy not a vector quantity? So in that case, you remember that when you multiply two vectors, okay, when you take a dot product of two vectors, it is a scalar quantity. So therefore, we can safely assume that the kinetic energy is a scalar quantity. Now, how did we get this formula? So let's try to understand where does this formula come about? Or how does this formula come about? Let's look at that, okay? Let us consider a given situation here where the mass of an object is m, okay? Initial velocity is 0, and it covers certain displacement s because of the application of force F, and finally it reaches the velocity v, final velocity v. Okay, so in this case, we know that the work done here is very simple, right? It's force times the displacement. So force times the displacement. So that's how we define the work to be. So what is the acceleration of this object here when it covers a displacement s and it has a final velocity v and initial velocity u? So from Suvat, okay, we know that v squared equals to u squared plus 2as, right? And because the initial velocity is 0, I can cancel this out. So u squared is 0. And then I simply have here that the acceleration is v squared over 2s. So this is the acceleration of this object when it goes from u equals to 0 to u equals to v. Now we know that from the definition of the work, we know that work is force times the displacement, right? So what I will do now is I will substitute this a in this definition of the work. So now because we know that the work is defined as force times displacement and force is defined as mass times acceleration, so I can write, instead of force here, I can write this as ma, right? So m times a. So m is the mass of an object and a is the acceleration of the object times the displacement. And mass times acceleration here is v squared over 2s. So v squared over 2s times s here. Now I can cancel this s's here and finally get work as 1/2 mv squared. So now having done a work of F into S increases an object's velocity up to V, right? So in fact, we can say that this energy, the work that we do, has been stored in terms of kinetic energy here then, okay? Because the work is defined in terms of velocity, we call this as the kinetic energy now. Energy because it's moving. So the work that you put on an object to increase its velocity to v stores the energy in terms of the motion, and that energy is basically what we call as a kinetic energy then. Okay, so this is how we define the kinetic energy then to be 1/2 mv squared. So that's it from the kinetic energy. So let's look at the last part of today's topic here. So that's work kinetic energy principle. So now let's assume that the initial velocity of an object is u. Okay, the initial velocity of an object is u, and because there is some force applied on the object, it reaches a velocity v after some time, after having covered certain displacement s. Now, the point is that the work kinetic energy principle basically states that the work done by the net force F, so this is the net force here. So the work done by the net force F on the object is equals to the change in the kinetic energy. Now, you know that the initial kinetic energy of this state. So when it's moving at u, you know that the kinetic energy is 1/2 mu squared, right? And when the object is moving with a velocity v, you know that the kinetic energy at this point is 1/2 mv squared. So when the force, net force F, does some work on this system, that work has to equal. Okay, so let's say W is the work done by the net force F. So that has to equal to the change in the kinetic energy. So the final kinetic energy is 1/2 mv squared, but you already started with 1/2 mu squared, right? So the difference in the kinetic energy then is equal to the work done on the system. So the change in kinetic energy is basically 1/2 mv squared minus 1/2 mu squared, right? So the final kinetic energy minus the initial kinetic energy. So this is basically the statement of work kinetic energy principle. Now we can use this statement to basically simplify our problems. So we'll look at one of the problems where we can apply this one, and then after that, we'll wrap up with this topic. So let's look at this question here. So you're given an object. Okay, so there's an object here. It's already moving at 30 meters per second, right? So initial velocity is 30 meters per second. And the final velocity here is then 50 meters per second. Now we want to find what is the work done in moving an object from 30 meters per second to making it to move at 50 meters per second. So now the work energy principle basically tells me that the work done on this system will be equivalent to the change in kinetic energy, right? So change in kinetic energy. So the change in kinetic energy is final kinetic energy here, right? So let's say this is kinetic energy final minus kinetic energy initial. So my final kinetic energy is basically then the work done is basically then given by final kinetic energy is 1/2 m here is 3 kg times final velocity is 50, so I'll write 50 squared minus 1/2 times 3 times 30 squared. So this, upon simplifying, you will get the kinetic energy, so which is 2400 joule. So that's the work done for an object to go from 30 meters per second to 50 meters per second. Now let's try to do another similar question, but this time we're using the work done. We're using the concept of the resistive force, but the work done by the brake. Okay, so in this question, you just have to find the work done by the brakes in braking 730 kg car to a rest in 80 meters. So you have a road here. Let's say this is the ground and this is the car. So it has an initial velocity of 32 meters per second. And because we want to bring a car to a rest, so the final velocity of the car will be 0, right? So we want to find the work done in this situation. So it has to go from 32 to 0 meters per second. Now, according to the work energy principle, we know that the work done by the brake in this case will be the change in the kinetic energy, right? So that's that was the statement of the work energy principle. Now, what we can do is change in the kinetic energy is basically EK final minus EK initial, right? So what is the final kinetic energy here? So this is the final state. So the energy kinetic at this point here, final is 0, right? Because the velocity is 0, so this becomes 0. But in this case, the kinetic energy initial is not 0. So this simply becomes 1/2 mv squared. So in this case, it's 32 squared. So that's what I write here. So final is 0 minus 1/2, let's say m here is 730 kg times the velocity squared is 32 squared. So my work done then becomes around 370,000 joules. Okay, 70,000 joules. This is in 3SF. Okay, or maybe this is in 2SF. Let me just check here. So that's in 2SF. Okay, now the work done here basically required only the knowledge of the kinetic energy here. So here the displacement was irrelevant. Okay, so whether you use the displacement or not, it becomes irrelevant here. But you could still do it using the SUBAT, finding the acceleration, finding the force, resistive force, and then multiplying it with the displacement to find the work. But having information about the end quantity here is sufficient for us to find the work done. So this is the work done by the brake. Okay, and because the work is negative, we know that the force and the displacement was in opposite direction. Okay, so we'll do that much for today. I'll see you all in the next lecture. Next time we'll talk about the potential energy.